All right, ladies and gentlemen, we just talked about what Newton's second law is. Now let's talk about how we're going to solve problems dealing with Newton's second law. Well, first thing we have to draw, right, if it asks for, and if it tells us about forces, we're going to have to draw a free body diagram. Right? We all know how to draw a free body diagram. There's 4 components of a free body diagram, right? Always make a box. You always have Fg going down, right? That's the force due to gravity or the weight. You have F sub n, you have the normal force going up. You have some applied force. And then no, the frictional force always goes in the opposite direction of the applied force. Always in the opposite direction. Well, then we get to the point where we say that any forces that don't line up in the x and y direction, right, or the axes, we break those forces into the components. If we look here, these right here, all these forces are in either the x, or the y direction. If we look here, if we have some 10 newtons of force pulling, right, and it's not exactly going in the x or the y direction, just like angled projectiles, we have to find the x component and the y component of the forces. So to solve for the force in the x direction, you have to do a cosine theta. To solve for the force in the y direction, you have to do a sine theta. Then you can go about solving your problem. Do not forget, when we have something that's at an angle, you have to break it up into its components, the x component and the y component. Number 3, then you can calculate the net forces in both the x and y direction, right? Remember, when we're talking about net forces, if they are in the same direction, you add them. If they're going in the opposite direction, I don't know why I just said that, the opposite direction, you subtract them. Do not forget that vector addition. And then number 4, you can solve the problem. Well, let's look at a couple of examples before you guys start your worksheet. Example 1. Which graph best represents the motion of an object that is not in equilibrium as it travels along a straight line? Well, first off, what is it to be? What do you say? How do you cause the object to stay in equilibrium? What do we know about an object that is in equilibrium? Well, we know that for an object to be in equilibrium, we must know that the F net is 0. If the F net is 0, our net force is 0, well, then that tells us that there's no acceleration. So there must be no acceleration for an object to be in equilibrium. Well, we have 2 cases. What are the 2 cases again? You guys know, when something's at rest or constant, it's traveling at a constant velocity. Right? Those are the 2 cases that we have no acceleration. Well, let's look at this. Let's look at A. What A graph is telling me is that our distance is not changing over time. So what does that tell us? We are at rest. So this is at equilibrium. So we do not want this. What is B telling me? As time goes on, our speed is not changing. So if our speed is not changing, we have a constant speed. That is at equilibrium. We do not want that one. Well, let's look at C. C says, as time increases, our speed increases at a constant rate. So we're increasing speed at a constant rate. So this is telling me that we now have an acceleration. We have an acceleration. Our speed is changing as time goes on. So therefore, this object is not in equilibrium. So this is what we want. D says as time increases, our distance increases at a constant rate. So this right here is telling me that we're traveling at a constant speed. So we do not want that one. Ladies and gentlemen, it's very important that we are always remembering what we talked about in the previous units because we're always going to be connecting it to the next topic. Right? This was motion graphs. We talked about motion graphs. And now we're applying it to talk about forces. Number 2, a force of 25 newtons east, and a force of 25 newtons west act concurrently on a 5 kilogram cart. What is its acceleration? Well, what does concurrently mean? That means same time. Well, let's break it up. Let's draw a little free body diagram. It says we got 25 newtons going east, 25 newtons going west. And it asks, what is its acceleration? Well, we know that our equation is A equals F net over M. So what must we have to solve for the acceleration? Well, we have our given, right? Our mass is 5 kilograms. If we look for the net force, we have to do vector addition here. So we're going to say 25 newtons, right? I'm going to go into the right positive. So 25 newtons minus 25 newtons gives you 0 newtons. So really in our heads, thinking, if we have a net force of 0, is our object accelerating? No, it's at equilibrium. So just to prove that to you guys, we have F net equals 0 newtons. Well, now let's plug that into our equation. A equals 0 newtons over 5 kilograms. Well, this is anything divided by 0 is 0. So our acceleration here is 0 meters per second squared. There is no acceleration. Our object is at equilibrium. Moving on to number 3. Now, number 3 is a tricky one. It says a 0.15 kilogram baseball is moving at 20 meters per second and is stopped by a player in 0.01 seconds. What is the net force stopping the ball? Well, there's a lot to break down. So let's write out our given. What are we given here? It says a 0.15 kilogram, so that's our mass. Baseball is moving at 20 meters per second and then is stopped. Well, what is this 20 meters per second? Right, that's a speed, and that says it's stopped, so that's another speed. And that gives us a time. What is the net force? So we're trying to solve for net force, ladies and gentlemen. Well, if we're looking here, we only have one equation that has net force in it, and we know that A equals F net over M. Well, do we have our acceleration here? No, it doesn't tell us straightforward what the acceleration is. But remembering kinematics, they give us enough information to solve for the acceleration. They give me an initial velocity of 20 meters per second, and it is stopped, so it comes to a rest, right? A halt. So that's VF equals 0 meters per second. And then they give you a time, 0.01 seconds. Well, you know, and you remember, that we have an equation for acceleration, right? One of these equations we use so much is VF equals VI plus AT. VF is 0, VI is 20 times 0.01 plus A times 0.01. Well, now plugging that into your calculator, 20 times 0.01 is 0.2 plus 0.01A. Well, let's minus the 0.2 to get that to the other side. So we have a negative 0.2 is equal to 0.01A. We have to get A by itself now. So divide by 0.01, divide by 0.01. A is going to give you 20 meters per second squared. A negative 20 meters per second squared. So what that's telling me is, if I'm throwing my baseball to the right, 20 meters per second, that when it stops and it hits the glove, it has a negative acceleration. It is slowing down, right? It's going in the opposite direction, right? Once it stops here, it has an acceleration going this way. All that negative means is it's going in the opposite direction. Well, guys, now I found the acceleration. I know the acceleration is negative 20 meters per second squared. Now we can plug it back into our equation. Negative 20 is equal to our F net all over your mass, 0.15. Multiply by 0.15, multiply by 0.15. F net equals a negative 3 newtons. A negative 3 newtons. So to stop this ball, we need a force, an F net, of 3 newtons, right? Again, all that negative sign means is that you're going in the opposite direction. The opposite direction. And this makes sense because in our notes, we said that the F net direction is going to equal the A direction, right? We said that the F net direction is going to equal our A direction. Good. Now notice, you're going to have problems where you may have to use an equation to solve for the acceleration. You may not just be given the acceleration. And now let's look at one more. This is a little bit of a simpler problem. You push your 1,000-kilogram car, given an acceleration of 0.05 meters per second squared. What is the net force? Well, let's just go right for it. Let's write out our given. Right, we have acceleration, 0.05 meters per second squared east. We have our mass, which is 1,000 kilograms. We're trying to solve for F net. Well, we know that A is equal to F net over M. A is 0.05. F net is what we're trying to solve for, and the mass is 1,000. Well, multiply by 1,000, multiply by 1,000. F net for this car, right, the net force applied is 50 newtons, and it is going to the east. Going to the east. Again, the force goes in the same direction as the acceleration. All right, ladies and gentlemen, take a look at these examples and use these and your notes to help you complete your worksheets. Have a good day.